Welcome to the deep dive. Today we are diving deep into, well, the fascinating world of how large language models actually learn to reason.
Yeah, it's a really interesting area. We've got some great sources lined up for you today.
We do. There's this groundbreaking research paper, Beyond the 80-20 Rule. High-entropy minority tokens drive effective reinforcement learning for LLM reasoning. Bit of a mouthful, but important.
Definitely. And we also have this brilliant demonstration of an LLM tackling a complex math problem step by step. It really brings the ideas to life.
So our mission today, yours and mine, is really to unpack these sources. We want to get to a new, maybe surprising perspective on how these LLMs actually think or reason.
Exactly. We're going to focus on which specific parts of their thinking process really matter most for learning, and then see that idea in action with this math challenge.
The goal is to give you a kind of shortcut to understanding some pretty cutting-edge AI research, and hopefully you'll have that aha moment about what these models can do.
Let's jump in.
Okay, so the research paper. It's all about this technique called reinforcement learning with verifiable rewards, RLVR for short.
Right. RLVR is, well, it's a really powerful method people use to make LLMs better at complex reasoning tasks. Think math problems or writing computer code.
We know it works, right? The models get better. But this paper asks something deeper. Why does it work? And how exactly, down at the level of the individual words or tokens, the model generates?
And their answer, it introduces this really insightful concept, token-entropy.
Okay, entropy. Sounds a bit technical.
It is, but the idea is pretty intuitive here. Think of token entropy as the model's uncertainty about what word or part of word, what token it should generate next, as it's thinking through a problem.
So low entropy means it's pretty sure what comes next,
Yeah.
like finishing a common phrase.
Exactly. Low entropy means high certainty, predictability. High entropy, on the other hand, means more uncertainty. The model sees several different tokens as being plausible next steps.
Got it. So they looked at these thinking processes, the chain of thought, the COT.
Right, the step-by-step reasoning. And their first big observation was that actually most of the tokens an LLM generates have low entropy.
Huh, really? Most of them?
Yeah. These are the sort of routine parts, finishing sentences, following standard math notation, basic code syntax. The paper calls them tokens that just follow the path. Predictable stuff.
There's always a but.
But yeah, they found a small fraction of tokens that have really high entropy. And these aren't just random blips, they're critical decision points. Moments where the model could genuinely go in different directions with its reasoning.
Okay, so these are the important moments. The paper calls them
Forking tokens. It's a great name, actually, because they literally steer the reasoning down one path or another, like forks in the road.
internal crossroads in the model's thought process. Can you give some examples? What do these forking tokens look like?
Sure. The paper mentions things like words introducing contrast, weight, however, and less, or progression thus also, causality markers like since, because.
Okay, makes sense.
And in math specifically, think about words like suppose, assume, given, or define. These are points where the model is choosing how to set up the problem or which strategy to try. Real decision points, real forks.
That makes a lot of intuitive sense. You know, a predictable step is just execution, but deciding how to tackle something or what to do when you hit a contradiction, that feels like a real choice.
Precisely. And they didn't just theorize this, they tested it.
How? How do they confirm these forks were actually important?
They did something pretty clever. They played around with the model's temperature. Now, temperature is this setting that controls randomness or creativity in the output, and it's directly linked to entropy.
Okay.
So what they did was selectively increase the temperature, basically, increase the uncertainty or exploration only for those specific high-entropy forking tokens. And guess what?
Performance got better.
Performance improved. Reasoning got better. But, and this is key, if they increase the temperature for the low-entropy predictable token,
Performance dropped
significantly. So it really confirms that having that beneficial uncertainty, that exploration at the decision points is what helps, not just randomness everywhere.
Wow. Okay, so these high entropy forks are definitely critical. Now, how does RLVR training the process meant to improve reasoning actually connect with these entropy patterns?
Well, their analysis showed something interesting. RLVR training doesn't fundamentally change where the high and low entropy points occur. The model still generates the predictable stuff, predictably.
Right.
But, and here's the crucial finding, RLVR primarily seems to change the entropy, or maybe the choices made, at those high entropy tokens. It's fine-tuning the decision points. making the model better at picking the right path when it faces one of those forks.
So RLVR isn't just about rewarding the final answer being correct.
Not just that, no, because it uses verifiable rewards, it can actually get feedback on the intermediate steps, on the logic along the way.
Oh, okay. So it can tell if a particular step, maybe even one of these forks, was a good or bad move.
That seems to be the idea. The verifiable part lets the training check that internal logic. And it looks like RLVR uses this detailed feedback really effectively to adjust the model's internal policy, its choices specifically at those high-entropy uncertain moments.
It's nudging the model toward better choices when it's genuinely unsure, rather than just reinforcing the easy stuff it already knows.
Exactly. It's making it smarter at navigating uncertainty.
Okay, this is where it gets really fascinating. The title of the paper, Beyond the 80-20 Rule. What do they find when they actually restricted where the learning happened during RLVR?
This is the kicker. It's pretty counterintuitive. They experimented with applying the learning updates, the policy gradient updates, which is basically how the model learns from feedback.
Right, the mechanism that adjusts the model based on whether it did good or bad.
Exactly. They tried applying those updates only to the top 20% of tokens with the highest entropy, just those crucial forks we talked about.
Okay, and what happened?
It worked just as well as, or sometimes even better than, training on all the tokens, 100% of them.
Wait, seriously? They only let the model learn from 20% of its own thinking steps, the most uncertain ones, and performance was the same or better.
You got it. For one model, the Qwen 38B, focusing on that top 20% matched the performance of training on everything. But for the bigger models, the 14B and 32B,
It was better.
significantly better. Like for the 32 billion parameter model, training on just the top 20% high entropy tokens boosted performance by over 11 points on one tough math benchmark, AU25, compared to training on all tokens, over 7 points on another.
That's actually wild. So less training computation, potentially, but better results, especially for the bigger models.
Completely changes the picture, doesn't it? It suggests that for improving reasoning with RLVR, it's not about brute force updates everywhere. It's about smartly targeting these critical, uncertain decision points.
And what if they tried the opposite? Training only on the easy, predictable, low-entropy tokens.
Performance plummeted. As you'd expect, maybe. It confirms those predictable tokens just aren't where the leverage is for improving complex reasoning. That learning needs to happen at the forks.
So the hypothesis is, focusing on these high-entropy forks helps the model get better at exploring different, maybe better reasoning paths when it hits a point of uncertainty.
That's the strong conclusion, yeah. It helps the model learn to navigate those tricky moments more effectively. And they found that around 20% seemed to be a sweet spot in their experiments, a good balance for exploration.
And you mentioned the scaled with model size. The bigger the model, the bigger the benefit from this focused training.
Yes, the advantages were more pronounced for the larger models. It suggests this might be a more efficient way to harness the extra capacity of bigger models specifically for reasoning tasks.
Interesting. Any hints about generalization?
A little bit. Even though the training was focused on math problems, they saw some improvement on a coding benchmark too. It hints that maybe these high-entropy tokens are tied to some more fundamental problem-solving or reasoning abilities that can transfer.
Okay, this is super interesting conceptually. High-entropy forks are key learning zones. But what does this actually look like when a model is solving a problem?
All right, let's make it concrete. This is where that math problem example from the source material is so helpful. It gives us a window into the model's step-by-step thinking.
It's like seeing the gears turn.
Pretty much. It shows the model navigating these paths and, crucially, hitting one of those forks and figuring it out.
So let's set up the problem for everyone. We need to find the sum of squares of a list of positive integers.
Yeah, and there are 3 specific conditions the list has to meet. First, the sum of the integers is 30.
Okay, sum 30.
Second, the list has a unique mode, and that mode is 9. So 9 appears more often than any other number, and no other number appears as frequently as 9.
Unique mode 9.
Got it. And third, this is the tricky one. The median of the list is a positive integer, but that integer is not actually in the list itself.
Okay, median integer and median LS. That does sound tricky.
So the LLM starts out, quite systematically. It defines the terms mode median. It understands the conditions.
Makes sense.
Initially, it makes what seems like a logical deduction. It thinks about the median. Usually, for a list with an odd number of elements, the median is the middle element, right? It's in the list.
Yeah, that's a standard definition.
So the model initially thinks, okay, the median must be an integer not in the list. Maybe the list has to have an odd number of elements, but somehow the median isn't there. It starts down that path.
Following a standard assumption.
Exactly. But then you can almost see the wheels grinding. It hits that fork we talked about. The logic bumps up against that specific condition. Median is an integer not in the list.
It realizes something's wrong with the initial assumption.
Yes. The text shows this internal monologue. It's quite striking. Things like, wait, but how can the median not be in the list if it's the middle element? Then, wait, maybe I made a mistake.
That feels like a high-entropy moment right there. Real uncertainty. The default path led to a contradiction with the rules.
It's a perfect illustration. This is where a forking token would likely occur. The model has to pause, reevaluate, and explore an alternative. It thinks, wait, unless the median is calculated differently.
And figures it out.
It does. It has this moment. It realizes if the list has an even number of elements, the median isn't a single element in the list. It's the average of the two middle numbers.
Right. And that average can be an integer.
And that integer average might not be one of the numbers actually present in the list. So perhaps the list has an even number of elements. That's the crucial turn. It successfully navigated the fork by correcting its interpretation.
Brilliant. Okay, so now it knows the list must have an even number of elements. What next?
From there, it becomes much more systematic. It starts exploring possibilities, beginning with the simplest case, an even number, n equals 4 elements.
Okay, n equals 4. How does it apply the conditions?
Well, for 9 to be the unique mode in a list of just 4 positive integers, you absolutely must have exactly 2 9s.
Makes sense. If you had 3 9s, the fourth number would have to be different. Some wouldn't be 30. If you had only 1 9, it couldn't be the unique mode.
Right, and the other two numbers, let's call them x and y. They must be different from 9, and they must be different from each other. Otherwise, 9 wouldn't be the unique mode.
So the sorted list looks like xy 9 9, where xy 9.
Exactly. Now apply the sum constraint. X plus y plus 9 equals 30.
Okay, so x plus y plus 18 equals 30, which means x plus y equals 12.
Perfect. Now, the median condition for the list, x, y, 9, 9. The two middle elements are y and 9. The median is their average, y plus 9, 2.
And this median, y plus 9, 2, must be an integer, and it must not be equal to x, y, or 9.
Correct. And since we know y 9, y plus 9 must be less than 18. For the average, y plus 9, 2 to be an integer, y plus 9 must be an even number.
Which means y itself must be odd.
Precisely. So now we're looking for pairs of positive integers, xy, such that x plus y equals 12, x, y, y, 9, and y is odd.
Okay, let's test the possibilities for y. Odd and less than 9. If y 7.
If y 7, then x equals 12, 7 equals 5. Does this fit? X, y, 5, 7, y, 9, 7, 9, yes. So the list is 5, 7, 9, 9.
Let's check the median condition for 5, 7, 9, 9. Median 7 plus 9, 2, exceeding 2 equals 8.
Is 8 an integer? Yes. Is 8 in the list? 5, 7, 9? No.
It works. All conditions met. Sum equal 5 plus 7 plus 9 plus 9 plus 9. Median equals 8, which is an integer not in the list.
Bingo. The model found it. It might quickly check other possibilities too. What if y was another odd number less than 9? Like y 5?
Then x will 5, 5 was 7. But we need xy, and 7 is not less than 5. So 7, 5 doesn't work in sorted order x, y, 9.
What about y 3, then x 9? But we need x, y, and y 9, and x can't be 9. Invalid. What about y 1? Then x 11 doesn't fit x, y 9.
So it seems 5, 7, 9 is the only solution for n4 that works.
Yeah.
The LLM likely confirms this.
Yeah, the source indicates it does some brief checking like this, considering maybe cases like a A99, which fails the unique mode condition, just to solidify that 5799 is the solution it's confident in.
Okay, and the actual question was for the sum of the squares.
Right. So for the list 5, 7, 9, the final step is calculating 5 squared plus 7 squared plus 9 squared plus 9 squared.
It's 25 plus 49 plus 81 plus 81.
Which adds up to 236.
There we have it. So bringing this example back to the research paper again, that whole process, especially that moment of realizing the initial assumption about the median was wrong.
Wait, maybe I made a mistake. So perhaps.
Yeah. That perfectly shows one of those high-entropy reasoning forks in action, a point where the model had to question itself, explore an alternative path based on the constraints, and make a critical correction to find the solution.
It really does. It's a practical demonstration of navigating those forks. And the paper's insight is that RLVR seems particularly good at training the model to get better at precisely these kinds of non-obvious turns and corrections, not just reinforcing the straightforward steps.
Okay, so let's synthesize. This deep dive really gave us a, well, pretty surprising insight into how LLMs learn to reason.
It's not just about uniformly getting better at everything. That's the core takeaway from this research. It seems a small, specific fraction of the thinking process.
Those high-entropy tokens, the forking points.
Exactly. Those moments of uncertainty and choice are where the most effective learning happens, especially when using RLVR. The model learns to handle ambiguity and make better decisions at the forks.
And we saw that play out so clearly in the math problem, that correction about the median condition that was navigating a fork, and it was essential to actually solving it.
Understanding this helps demystify these models a bit, I think. Improving their reasoning isn't just about throwing more data or bigger models at the problem, though that helps too. It's also about finding these more elegant, targeted ways to optimize the really critical junctures in their thinking.
Focusing the learning where it counts the most.
Precisely. It's about improving how they navigate uncertainty.
So here's a final thought for you, our listener, to maybe mull over building on all this.
Yeah.
If focusing the learning signal on just 20% of the tokens, these critical decision points, is so dramatically effective for improving complex reasoning in LLMs, how might we apply that same principle? You know, the idea of identifying and really leveraging the crucial moments of choice or uncertainty. How could that apply to other complex AI tasks?
Or even how we learn ourselves. Could focusing on our own forking points make our learning more efficient, more powerful?
Something to ponder indeed.